All right, this is section 14.9, which is on parameterization of surfaces. So this is sort of an odd section in the sense that it was added to the textbook maybe 10 or so years ago because of some redoing of how things were introduced. And so it's an odd section in the sense that it doesn't really belong in chapter 14. It's necessary for chapter 15. The reason it's not in chapter 15 is because chapter 15 is sort of heavy enough already with enough stuff. So it usually gets tagged on at the end of chapter 14, but it sort of stands alone, separate from the rest of the material. So, by way of intro, let me just sort of remind you of what it means to parameterize a curve. So, to parameterize a curve, what this means is, it means to give a function r of t, let's give a specific example. R of t is, say, t squared I plus 2tj with a range of t's, often. Let's say t between 0 and 2. And what happens is we think that, like, for each t we plug in, we get a vector. We think of the vector as a point, and we plot all the points. So for each t, we get a point. So for example, e.g. r of 1 is 1i plus 2j. We think of these as points. We think of 1, 2, we plot it. And all the points together give a curve. So in this example, we would have something like the following. So when t equals 0, we're at 0. When t is 2, we're all the way at 4, 4. It's 4, 4. When t is, say, 1, we're at 1, 2. So we're right here. So if we plot this, if we plot all of these, it does something like this, and this is the curve. So C is the curve. Now, normally we think of t as like a time variable, and we think of this object, we think of this as an object moving, but that's not really relevant, right? So it doesn't really matter. If we're just describing the curve, using t doesn't matter. Like, we don't need to use t. Right, so we could write, we won't, but I'm going to do this just because it'll help see what happens when we go to a surface. We could, like, write r of u is u squared I plus 2uj for u between 0 and 2. Right, there's no difference. Right, same curve. But the point is that each t value or u value or whatever variable we plug in gives us a point. Put those points together, we get a curve. So what we want to do in this section is figure out how to do that for surfaces. So, definition. So to parameterize a surface, and typically curves are called C, just for a generic name. Surfaces are generally called sigma, sometimes S, but I'm going to use sigma. This is the notation. It's not a sum. It's nothing like that. It's just a Greek letter that's used. So to parameterize a surface means to give a function. This will be r of u comma v. So we're going to have two variables to sort of pull out two dimensions. And so we'll have an I, j, and a k, typically. And each of the coefficients could involve the variables u and v. So we'll write x of u and v, I plus y of u and v, J plus Z of U and V, K. Same deal, we're going to give ranges for U and V. Those will typically be given by inequalities, just like for T. We'll see those as they come. And then the same thing holds, right? So we plug in all possible U's and V's, we get a bunch of points, and together they draw a surface. Right? So for each pair, U and V, we plug it in, we get a point. Or really, we get a vector which we treat as a point. So all the points together give a surface. Now, just one note before we dive into some examples. Is the U and the V, we never actually use letters U and V. Those are just sort of placeholders. Instead of U and V, we typically use letters that are familiar to us. So X, Y, Z, R, theta, phi, rho, those. So we never use U and V in practice. Or let's say in actual parameterizations. They're just abstract. Or really, they're just placeholders. So what we'll do is we'll typically use two of the following. X, Y, Z, all these familiar ones, R, theta, phi, and rho. And which two will depend upon the situation, as we'll see. Depend, let's say, on sigma. So what I'll do next is I'll do two specific examples that are custom chosen to show a very important point that needs to be made about parameterizing surfaces. And so once we can compare those two, I can make a comment, and then we'll just blow through a whole bunch of examples and see what comes up, and just practice, practice, practice. So let's take a look at two sort of really simple examples for starters. So we'll say two basic examples. And a note. So what I'll do for all of these examples is I'll describe the surface, I'll draw it, and then we'll sort of figure out what the parameterization could be. So for the first one, example, so the surface is going to be a small rectangle. So it's like a plane, but it doesn't go on forever. It's really just like this finite rectangle right here. We're going to put that sort of cornered up on the z-axis. We'll say that it'll extend in the x direction. We'll say it'll be maybe 1 unit long. It'll be sort of 2 units wide. It'll be 3 units high. It'll be at z equals 3. So it's kind of like a plane, but it's finite. Right? It's just 1 by 2. It's flat. It's up at z equals 3. And so what we see in this is we see that the x and the y, they vary between x goes between 0 and 1, y goes between 0 and 2, z is fixed. So two really good variables we can choose for this parameterization are just x and y. So we can parameterize as follows. So we'll do r of xy. We'll do xi plus yj plus 3k. We'll say that x goes between 0 and 1. Y goes between 0 and 2. And that's it, right? So if you plug in all these x's and y's, you get the rectangle when you think of them as points. So plugging in all these x and y gives the rectangle. as the parameterization. So now compare that. So what I'm going to draw is I'm going to have a very similar surface. It's still going to be up at z equals 3, but now it's going to be a disk. So let's say radius will be 2, for example. So it'll be centered on the z-axis. We'll say it's still at z equals 3. So radius 2 at z equals 3. So in this case, it doesn't make sense to use x and y, because if we have x and y with inequalities, we're going to get a rectangle. Right? Like there's no way around it if we have constant bounds. Now, there might be sneaky ways to do it, but right now, if our bounds are going to be constant, like x and y won't work. But then we look at this and we think like, well, this is circular, and we think about polar coordinates and how polar coordinates, we can do this with constant bounds, right? So when you look at this, you want to think like polar. Can it help? So the answer is, here's the parameterization. So I'm going to use theta and r. I'm going to make this x value r cosine theta, the y value r sine theta, the z value, or the k, 3, and we will have theta going from 0 to 2 pi, and r going from 0 to 2. So now when we plug these values in, these r's and thetas, we get the x's and y's that draw us the circle. Right? So plugging in for theta and r gives us the disk, let's say. So take a look at these, right? They're both sort of pieces of a horizontal plane, right? They're both pieces of the plane z equals 3. One is rectangular, and we're using x and y. One is disk-like, and we're using r and theta. So I just wanted to point that out so I can make the following sort of really concrete point. Observation I want to make here with regards to these two examples is both are pieces of z equals 3. However, the square, or rectangle rather, to be more accurate here, the rectangle has, it's going to sound redundant, but that's okay, has rectangular restrictions. So we use, if you like, rectangular coordinates here, x and y. The disk, let's say, has, let's say, circular restrictions, if you like. So we use coordinates that are familiar for that. So we use theta and r. And so the general point I want to make here is the following. Spelled wrong. General. Is surfaces basically have two aspects. They're a piece of something, like both of these are a piece of z equals 3, but they have restrictions as well. The top one has rectangular restrictions, the bottom one has disk-like restrictions. So it's very often the restrictions that influence the variable choice more than the thing that you're taking a piece of. So let's say the restrictions often, I would say more than half the time, dictate or let's say give us information about the variable choice. It's a polyphrase sentence. The restrictions often give us information about the variable choice more than the thing we're taking a piece of. That's just something to keep in mind. So with that, what I'll do is I'll dive through just a whole bunch more examples, and we'll see what comes up. But keep these things in mind. Keep that idea in mind that we're taking a piece of something, but we're also looking at the restrictions on the shape of the piece itself. Number 4, more examples. So I'm going to do some sort of modifications on the very first example, the rectangle. So let's do a slightly different rectangle. So let's let sigma be the following rectangle. This can be a rectangle, except it's going to be along the y-axis. Right here. So let's say we'll put it at, say, y equals 3. And we'll make it sort of like the first one. We'll make it, say, 1 unit high in this case, and 2 units in the next direction. So because the y's value is fixed here, and the x and the z vary, it makes sense to use those variables. So we can do r of x and z is xi plus 3j plus zk. And this will go with x between 0 and 2, and z, between 0 and 1. So nice and simple. So here's a different variation on that first example. So I'm going to have a rectangular piece of something. It's not going to be a plane anymore, it's going to be a paraboloid. So we'll look at, let's say, let sigma be the following. So what I'm going to do is, so bear with me as I draw this, I'm going to draw a big paraboloid. I'm drawing this in black because this is not sigma. Right? So sigma is going to be blue here. So this is the paraboloid, let's see, z equals 25 minus x squared minus y squared. So it opens down from 25. And the surface is going to be a rectangular piece of this. Think of like a band-aid on top of the surface. And so what we'll say is that this sigma will be between, say, it'll have rectangular restrictions on x and y. This is the piece. This is the piece of the paraboloid that has, say, x between 0 and 1. Actually, let's do 2 because it looks more realistic. And y between 0 and 1. So, how do you make that? That's kind of y between 0 and 1. So it's like a paraboloid patch, if you like. So, because we know what z is in terms of x and y, and because we know that x and y are rectangular, it still makes sense to use x and y. Right? So, what we can do for this is we can do still r of xy, still xi, still yj. And now here, we put 25 minus x squared minus y squared. And then we'll still do with, in this case, x between 0 and 1, or between 0 and 2 rather, and y between 0 and 1. So the x's and y's draw a rectangle, and then the z coordinate, the z value, let me label that right here, this puts it on the paraboloid. If you like, it puts the point on the paraboloid. But again, so think about what we said, this point over on the right, I erase it, this thing. The restrictions often give us more information. So the restrictions in this one are rectangular, so it makes sense to use rectangular coordinates, x and y. So what I'll do next is I'll take another piece of this same paraboloid, but a different shaped piece, and we'll see how that comes into it. So what we'll do is we'll say, let's let sigma be, so what I'm going to do is I'm going to take the same paraboloid, I'll take a disk piece of it. So Same exact thing here. But then the piece that we're going to take, we say a radius 2 disk. So it's like the cap of the paraboloid. Badly drawn paraboloid, but that's okay. So here sigma is the cap of this paraboloid. Say it's the cap. Let's say with radius 2. And just to be clear, what I mean by radius 2 is if you were to drop it down into the xy plane, you would get like a radius 2 disk here. But this is sigma up here. This is just for reference. Radius 2. So again, with this little conversation, we said, hey, it's the restrictions that often guide the variables. So if all you were doing is just the disk, right, like in the xy plane, if we ignore the z, right, we could do something like r of theta and r is r cosine theta I plus r sine theta j plus 0k. And this would be with theta between 0 and 2 pi. And r between 0 and 2. This guy, just for reference, while we have the picture available, this parameterization would be this disk. Right there. Because z is 0. So what we'll do instead is to put it on the paraboloid. And what we want is, we want z to be 25 minus x squared minus y squared. But we don't have x and y anymore. We have the things that went in for x. And so that here, x is the I component, which is r cosine theta, and y is the j component, which is r sine theta. So z is 25 minus x squared minus y squared, but that's minus r cosine theta squared minus r sine theta squared. Another way of thinking about it is x squared plus y squared is r squared. So this turns out to be 25 minus r squared. So for our final answer, we have r of theta and r, which is r cosine theta I plus r sine theta j plus 25 minus r squared k. This is with theta between 0 and 2 pi, and r between 0 and 2. And again, in this case, it's this third coordinate, this thing right here that puts it on the paraboloid. Puts the point on the paraboloid. And that's the 25 minus x squared minus y squared, where the x and the y are given by r cosine theta and r sine theta, respectively. So again, side by side, they're both pieces of the paraboloid, this one and the previous one, but the rectangular piece uses x and y, the disc-like piece uses r and theta. So let's look at a few more. Okay, for this next one, I just want to go back to the second one, just so we can have it on the screen, just to see. So let's say first, no, this is a big long parentheses. The second example that we drew was a disk. It was a disk up at z equals 3. So the small, it was z equals 3, and it was radius equals 2. And this thing had the parameterization r of theta r. It was r cosine theta I plus r sine theta j plus 3k. So it's with theta between 0 and 2 pi, and r between 0 and 2. So all I want to do is point out what happens if I want to change the disk slightly at the end of the parentheses. So consider now this. So it's still going to be a disk. Now I'm just going to dump it over on the y-axis. Otherwise, the numbers are sort of very, very similar. So this is on the y-axis. It's going to be at y equals 3, and radius 2. So probably you can see what's going to happen is now we'll just do r of theta r still. We'll just swap some coordinates out, right? Because this is now a disk in the x and z sense. So we could do r cosine theta I, put the 3 in the j component for the y value, r sine theta k. Still range, still the same range. So theta between 0 and 2 pi, and r between 0 and 2. Now, this might bother you because you might be thinking that I'm sort of doing something weird with polar coordinates, but the reality is I'm not really using polar coordinates. I'm just using what we know about polar coordinates to do a parameterization. And so the key thing to see here is that the variables are sort of dumb. They don't know. So the kicker is that these form a disk in the x, z sense. And then the 3 just makes it on in the y direction, the 3 units. So don't think about it so much as like, well, we're using polar coordinates. Like, well, we're not. We're smart, and we're using the same information that let us develop polar coordinates to do this as well. So nothing different there. We just did a disk in along the y-axis instead. So next one, I'll do something completely different. So let's take a look. This next example, what I'm going to do is a cylinder. So this will be a bit different than the previous ones, and we'll see why. So the cylinder will be stretched along the z-axis. So we'll go we'll say it'll go maybe up to z equals 5. I'll say the radius is 3. So in this case, this is the reason this is different than the previous examples. Is the previous examples always paired the variables together in a familiar way, like x and y, x and z, r and theta. This is different, right? So if you look at this, if we look at the two things that are changing, the radius isn't changing. It's a cylinder, it's hollow, right? So just so we're clear, this is hollow, and there's no caps on the end. So it's like a toilet tube, for example, like toilet paper tube or some kind of cylinder like that. So the radius isn't changing, it's not filled in, so I don't need an r. Right, radius is a fixed 3, but the z is changing. And so note here, radius is fixed. Sorry, I spelled radius with an e on the end for some weird reason. Is fixed. So we don't need r. But there's a theta that's changing. And a changing z. So what we'll do is we'll use those too. So it's an interesting mix. We'll do theta and z. So in the xy direction, we want a circle of radius 3. So we'll do 3 cosine theta I, 3 sine theta j. And before I finish it, I just want to point out that these form a circle in the xy plane. Right, that's a familiar circle. And what we'll do is, on the end of this, we'll add a zk, and this allows the circle to slide up and down for the different z's. And we'll say with, in this case, theta between 0 and 2 pi, z between 0 and 5. Then that'll draw the cylinder. For each z, we get a circle. All the circles together make a cylinder. And now, just before I do a final couple of examples, I just want to make a little note here. could have made it earlier, but now's a good time, is you might wonder, like, I did theta comma z, does it matter if I do theta comma z or z comma theta? And the answer is no. Once you choose it, be consistent, because, like within the problem, because in chapter 15, there'll be some places where once you make a choice, you want to stick to it for that particular parameterization, but it doesn't matter which you choose. So you could do r of z theta as well. But once you stick to it, see, once you choose for a problem, stick with it. Right, and we'll see why in chapter 15. Like, because we'll be taking these things and taking partial derivatives of them, cross products and so on. And so if you set your problem up with theta comma z, like, stick with that. If you set it up with z comma theta, stick with that. Same with x and y, same with r and theta. Sometimes people will do r comma theta, sometimes theta comma r. Doesn't matter. Just pick one and go with it, and don't change once you've chosen it for the problem. So let me just end on a couple more examples. So in this next example, I'm going to do just another cylinder, really easy one, except I'll do this one coming forward. So in other words, be like this. Forward in the x direction. So put the axis, and put the, say, the origin way back here, just for fun and excitement. And then we'll describe this thing. We'll say it goes between, say, x equals 5 and 10, and its radius is 4. And so we can probably see exactly what this is going to be, because now the circle is in the y-z sense, and the x is free to move. Right? So this is sort of, think of this as a circle in the y-z sense, with x free to move. So the variables that we'll use are x and theta. So I'll do theta and x just to be consistent with the previous problem, but it doesn't really matter as long as I'm consistent here. And we'll have an xi that takes care of the x direction. Then we'll have radius of 4, so 4 cosine theta j, 4 sine theta k. We'll list theta first, between 0 and 2 pi. And we'll list x next, between 5 and 10. That takes care of that. So, next example, what I'll do is actually, let me modify this one very slightly. Let's just take the top half of this. Previous problem. So, picture would be something like this. It would still have the origin axis would sort of poke out here, the x-axis. Origin still way back there. So in this case, we can use the same parameterization. It's just the range of theta that will change. So we have to sort of pay attention to that, right? It's the same, in other words, same r. Different theta range. So what we'll do here is I'll just relist it. xi plus 4 cosine theta j plus 4 sine theta k. Theta will go from 0 to pi. If you're not exactly sure why that is, that's alright. We'll clarify that in a second. X goes from 5 to 10 rather. So if you want to know about this, if you're curious why, the thing to look at is to look at the i's and the j's and the k's. So the 4 cosine theta j plus 4 sine theta k alone is this circle in the y-z plane, and it starts right over here. goes up and over, ends at pi right here. So if I just want the top half of that, we'll do 0 to pi, just like we would do in the normal xy plane. That gives us the top half of the cylinder in this picture. So let's just do 2 more. First one I'll do is a hemisphere. And I want to do this one because it actually can be done with 2 different parameterizations. So let's let sigma be the hemisphere. So just the top half of the sphere, center at the origin, nice and simple. So radius, let's say 5. So you have 2 choices here. So one thing is you might be like, well, look, it's kind of like a sphere, so why don't I use what I know about spherical coordinates to do it? And that would be fine. Right, so we can do... Now we don't need a rho, because rho is the distance from the origin, it's the radius if you like, that's a 5, that's fixed. We do need a theta and a phi. So what we know about spherical coordinates tells us that we could do 5 sine phi cosine theta I plus 5 sine phi sine theta j plus 5 cosine phi k. And then here we would have with theta going between 0 to 2 pi. Phi, remember phi is the angle that it makes with the positive x-axis. So phi would go from 0 to the xy plane, which is a pi over 2. That would draw the hemisphere. Or we can base this upon what we know about polar coordinates, right? Because the sphere has equation, right? The sphere is, the full sphere is x squared plus y squared plus z squared equals 25. So the hemisphere is z equals positive square root of 25 minus x squared minus y squared. So basically, this is kind of like a disk that has some z to it, right? Like a disk in the xy plane, but then the z has to be on the hemisphere. So we can do theta and r. It's technically a disk of radius 5 in the xy direction. So 5 cosine theta I plus 5 sine theta j. And then here we would need this z function just above, but I need to plug in what we know about x and y, so this becomes the square root of 25 minus r squared k. And then this would be with theta between 0 and 2 pi. And r in this case between 0 and 5. Oops. And it's the same as sort of before, is that the first two, the I and the j, form a disk. Right, so these guys are a disk in xy sense. And this guy puts it on the hemisphere. So either of these is fine. I'm not saying one is better than the other. The top one's a bit more confusing because it's got more trig functions. The bottom one has a square root. Personal choice depends on the situation. These are just options that are available. So let me just end with one more example. For that, actually a pretty simple example, but just using a different shape. So we'll say let sigma be the piece of the parabolic sheet. So I'll draw this. So what I'm going to do is I'm going to take the parabolic sheet. I'll draw the parabolic sheet in black, because that's not sigma. Right? It's just a piece of this. So this parabolic sheet will be, this guy will be just y equals x squared. That opens sort of up around, to the right around the y-axis. And so this is how I'll describe the sigma for you. So I'm going to take a little rectangle over on the left on the xz plane. That's not sigma. Right? So this is just a, say, let's say it goes 0 to 1 in the x direction, and say 0 to 3 in the z direction. And so the surface that we're interested in will be the piece of parabolic sheet that's to the right of this. So sigma right here is the piece of y equals x squared to the right of, I guess in this color it's yellow, or it's sort of a mustard color. Say the yellow, you don't like mustard, rectangle. You like mustard. Anyway, back to the surface. That's the sigma. So because the restrictions are rectangular in nature, we use rectangular coordinates. Because we know y is a function of x, it's good if we can avoid using y. Right? So let's avoid y because we know y equals x squared. So let's use x and z. So do x and z, xi, then we have y, but y is x squared, so x squared j. So those are parabola in the xy plane, and then ck, this will be with x between 0 and 1, and z between 0 and 3. So nice easy parameterization to end on. So that's the end of that section. It's the end of the chapter, in fact.